Let's talk about some other common network-related problems. First of all, we should say why. Well, networks are really common in real applications, and there are specialized algorithms for solving a lot of network-related problems that run faster than solving just a general linear program. So there have been cases where some linear program was really hard to solve until someone realized that, oh, hey, this big part of it is really just a network flow thing, and then they could solve it really quickly. So we've already talked about minimum cost network flow. Of course, you could also do like maximum profit network flow. There's a subclass called transportation problems that we'll talk about in a little while. Related to min cost network flow is shortest path. That's the problem that your computer or phone is solving if you say, give me driving directions from here to there. Two we haven't talked about are max flow. If all you care about is getting as much as possible from a source to a sink using whatever the current road capacities are, and you don't care about cost at all, you just want to maximize the flow, that's a max flow problem. That might be something where there's an emergency that needs supplies at one location and you have a bunch of supplies somewhere else and you just want to get stuff to that one place, as much stuff as quickly as possible. There's also something called min cut, which is interesting. If you have a road network with a source and a sink, like A and D in our city problem, and you want to completely disconnect the source from the sink by cutting roads, and you know the cost to cut each road, how can you cut some combination of roads at minimum cost to completely separate the network? It turns out max flow and min cut have a very interesting relationship, which we can mention later in the semester. Let's talk about something else called minimum spanning tree, which has its own interesting flavor to it. Let's say that these roads don't exist yet, and we want to build roads to connect the cities at a minimum cost, and I don't have to have a direct path between cities. I can have multiple hops to get from one city to another. So every city has to be on the network that we build, and we pay for building roads according to the cost shown here. So let's go show some possibilities there. So I could say let's build A to B, let's see, A to C, and A to D, B to D. And the cost for that would be $7 plus $3 plus $10. Or I could build, let's say, A to B, A to B to C, and B to D. Would I ever want to then throw in a link here? Well, that would provide faster service between C and D, but it would cost an extra $2. And in this problem, all we care about is minimizing the cost of building the network, not the cost of operating the network or the time it takes to get from one place to another. So we wouldn't throw in a link like this. We also wouldn't throw in a link over here. And so the optimal network that we build will not have any cycles in it. No place where you can get from a node back to itself by another place, because that implies that there's more links than I really needed to build. A network with no cycles in it is called a tree. So that's why this is the minimum spanning tree problem. Spanning means the network we build touches every node in the network. What else can we imagine here? We could say kind of a opposite version of what we just drew. We could also go, let's see, B to C, A to C, and B to D. That would be reasonable. And the minimum spanning tree problem is interesting because there are two algorithms for solving it, and each of them is greedy in some sense. It just says, of all the roads that I haven't built yet, which one is the cheapest that wouldn't start a new cycle, start a cycle in the network? And that idea that being greedy is good and then ends up being optimal is really nice when it happens, but it doesn't always happen, and that's what we'll talk about in our next video.